9th Standard ICSE Chemistry Chapter 3 from Prasad textbook, Water. The first few paragraphs are just general knowledge. Mark it as read. Now here we have a definition. Substances that contain water of crystallization are called hydrated compounds, like blue vitriol, CuSO4.5H2O. We'll study this in detail after a few pages. And if the water of crystallization is lost from such compounds, they are called anhydrous. For example, if we heat this copper sulfate, then the water of crystallization will evaporate and the blue crystal will become white amorphous, that is white powder. Now, water is a very special liquid. It's the only compound which exists in all three states on Earth under normal conditions. Water is a universal solvent. It dissolves solids, liquids, gases, so many salts. The reason is it has very high dielectric constant, meaning it has the ability to break bonds and dissolve substances. It's a polar covalent compound. Covalent because it is sharing of electrons, and polar because it has poles, a slightly negative hydrogen pole and slightly negative oxygen pole. And that's because the shared electrons are not symmetrically or equally shared. It's attracted more towards the more electronegative oxygen. Some compounds like methane and carbon tetrachloride, all the organic compounds, they are non-polar because there the electrons are shared symmetrically. There is no charge separation. Here there is a charge separation. So even though it's a covalent compound, it does have some properties of ionic compounds, and that is why it is able to dissolve ionic compounds like NaCl. NaCl dissociates into its ions and dissolves in water. Even HCl, it's a polar covalent compound, so even it ionizes, the bond breaks and it dissolves in water. So like dissolves like. So water can dissolve many ionic and polar covalent compounds, but it usually cannot dissolve the non-polar compounds like diesel, petrol, benzene, toluene, because those are non-polar, those are organic. So they will dissolve in organic solvents like carbon tetrachloride. In this chapter, we'll also study about solubility graphs and hardness of water. Let's start with solutions definition first. Mark the definition. It's homogeneous. Solute is dissolved in solvent. Mark the definitions of that. Homogeneous means it has a uniform composition throughout the volume of the mixture. We can't differentiate between them. For example, if we have sand in water, that's heterogeneous. Clearly, the sand can be seen separately from the water. Also, solution is always a mixture. There's no chemical reaction, so it's not a compound. If there's a lot of water in the solution, we call it dilute. And if there is less water, we call it conc. Learn these definitions word to word and don't use the word than in the definition. That will be wrong. Apart from the aqueous solutions, we can even have non-aqueous solutions where the solvent is not water. Solvent can be alcohol, acetone, carbon tetrachloride, etc. Alcohol is also a very good solvent. It dissolves all your sorrows. A lot of chemicals like iodine, naphthalene, chlorophyll, all of these things can dissolve in alcohol. Next, the definition of a true solution. It is one which is homogeneous. The particles of a solute and solvent cannot be distinguished from each other even under the microscope. There are some solutions which are not true solutions, which look homogeneous, but if we view them under a microscope, we would realize that it is actually heterogeneous. Such mixtures are called colloids. For example, air is a colloid. Yeah, right now the air looks transparent and homogeneous, but in a dark room, if we allow a beam of light to enter through the window, in that beam of light, what do we see? We see dust particles. This was a Tyndall effect because of scattering of light, because of which we could see it. Otherwise, normally we don't see the dust particles. But this proves that air is a colloid, not a true solution. Similarly, milk, blood, it looks so homogeneous, but in fact, they're all colloids. NaCl in water is definitely a true solution because we can't filter out the NaCl no matter what ultra filter we use. And even under a microscope, we can't see it, or there's no Tyndall effect to view the salt. So remember, a true solution is always clear and transparent. If it is colored, it is not a true solution, it's a colloid. And if it's heterogeneous, we call it a suspension. A true solution has particles which are very small, 10 raised to minus 8 centimeters in diameter, so small that they cannot be filtered out. We'll have to do distillation or something else to filter them out. Typically, the solubility of a solute in a solvent increases with temperature when the temperature is raised. So hot water can dissolve more salts than cold water, more salt than cold water. There are some exceptions. Unsaturated solution means at that temperature, it can dissolve more solute. And saturated means it cannot dissolve any more solute at that temperature. But sometimes we can force excess solute to dissolve in water. It's like you say that you are full, you cannot eat more, you just had your lunch. But when somebody gets a death by chocolate cake, you can still eat some of it, forcefully even. So then you are super saturated solution. Preparing a supersaturated solution involves slow cooling of a saturated solution at higher temperature. So since it was at a higher temperature, it had dissolved a lot. And now if we slowly cool it to the specific desired temperature, then the excess salt usually crystallizes out. But in certain situations and conditions, some salts do not crystallize out completely. Some of the excess salts remain dissolved. And then we get a supersaturated solution. Such supersaturated solutions are very unstable. If we stir them or shake them, then the excess of the solute will again crystallize out or precipitate out. Also, solubility can be increased by increasing the temperature mostly, but not by pressure. Even if you increase the pressure, the solubility doesn't change of salts. It can increase for gases, but also another way to convert a saturated solution into unsaturated solution is by adding more solvent. Now, solubility. Mark the definition. In 100 gram of solvent, how many grams of solute can dissolve at a particular temperature and pressure? That is solubility. No formulae, no calculations. Cancel this as well. This is cancelled as well. Now remember, when temperature increases, mostly the solubility of solids increases, but the solubility of gases decreases. So when you boil water, the gases which were dissolved in it will now start escaping. That is why you see bubbles coming out of it. And that is why boiled water doesn't taste that great. It tastes very bland because the taste which is imparted by the dissolved gases is no longer there. And boiling will not evaporate the minerals, okay? Just the dissolved gases will evaporate. Increasing the pressure will increase the solubility of gases. That is why in soft drinks, excess carbon dioxide can be dissolved under great pressure because that dissolved carbon dioxide gives soft drinks a pleasant taste. If all the fizz is gone and all the gases have escaped after opening the cap and releasing the pressure, then it's just like sweet water that doesn't taste that great. Nevertheless, don't drink soft drinks, it's not healthy. Drink lemonade. Learn these solvents which can dissolve these solutes. Solubility curve, mark the definition. It's a curve which helps us to understand the solubility of a salt at different temperatures. Have a look at this one. It's very useful to compare the solubility of different salts and understand their behavior. Calcium sulfate is quite exceptional because its solubility decreases as temperature increases. Otherwise, solubility always increases. NaCl's solubility almost remains the same. It's flat. It increases slightly. Potassium nitrate's solubility increases very rapidly as the temperature increases. You should be able to read the graph. So if you ask me the solubility of potassium nitrate at 60 degrees Celsius, I would say it is between 90 and 100, say 95 gram in 100 gram of water. Mark this as read, and this is also read. Don't cancel it, just read it. These calculations are cancelled. Now, water of crystallization. First of all, what is a crystal? Mark this definition, but mark it as read, meaning I will not ask it in the test, it's not that important. But in school, if teacher insists that it is to be learned, then do it. It has a particular shape with sharp edges and plane surfaces. Crystallization, mark the definition, and even water of crystallization, mark it as IMP. Also mark the definition of hydrated salts and anhydrated salts. For example, this is hydrated CuSO4.5H2O. The dot means a weak bond. Anhydrous means without the water of crystallization. So it does not have the dot 5H2O. And if you add water, again it becomes blue crystals. That's the observation. It's a chemical change. And it's also a test to prove that this liquid is water. There are many crystals which don't have water of crystallization. For example, sugar, NaCl, etc. And there are many anhydrous substances which could never have water of crystallization, like talcum powder. Mark this paragraph as read. Remember, amorphous means powdery and anhydrous means without water of crystallization. If you want to get rid of the water of crystallization from hydrated substances, you can either heat it or you can add conch sulfuric acid because it's a dehydrating agent. It absorbs all the moisture present. Now, two technical terms, efflorescence and deliquescence, mark the definitions. Imagine you have some hydrated crystals of washing soda, that is sodium carbonate decahydrate, or even blue vitriol. If you heat it, the water of crystallization evaporates, and you are left with the amorphous, anhydrous form of it. But even if you don't heat it, if you just expose it to air, slowly the water of crystallization will evaporate, converting the crystal into its amorphous anhydrous state. And this phenomenon is called efflorescence. This happens only when the atmosphere is dry and the temperatures are high. Deliquescence is the exact opposite. Some substances like ferric chloride, if you leave it on a table, they absorb the moisture from the air and become a saturated solution. It's almost as if somebody spilled water on it. So this property is called deliquescence, and that is why such substances are usually stored in an airtight container. Otherwise, they'll just absorb moisture and become a saturated solution. All of them are solids, and such deliquescence is maximum when temperatures are low and atmosphere is humid. Now, the table salt that we eat at home, it's not deliquescent, yet it becomes moist in humid conditions on a rainy day. That's because it is not pure NaCl. It has some impurities like magnesium chloride and calcium chloride, which are deliquescent. So mark this as a GR. Now, hygroscopy, mark this as a definition. There are some substances like anhydrous calcium chloride as against the hydrated ones. And even conch sulfuric acid, that's a solution. Phosphorus pentoxide, solid state or fused state. In both the cases, they absorb moisture, but unlike deliquescent substances, they don't change their state. They maintain their state, which is solid or liquid state. The solids don't become saturated solutions like deliquescent substances do. So these are called hygroscopic substances. You know that silica gel sachets are used in suitcases or new bags where they absorb the moisture to prevent the growth of fungus in them. So mark this as a GR and this one as well. So these hygroscopic substances are used as drying agents to dry things, dry gases in the labs, etc. We can't use deliquescent substances because they will just become saturated solutions. Next, drying agents versus dehydrating agents. Drying agents remove moisture, and that's a physical change. But a dehydrating agent, they absorb moisture even if water is not even there. Their willpower is so high that they will break the bonds in the chemical and create water and then absorb that water. So it's a chemical change. Look at this equation. Sugar. Sugar crystals have no water. But conch sulfuric acid is such a powerful dehydrating agent. It has such affinity for water. It will break the bond between carbon and HO, create water out of the HO, 11 molecules are formed, and a black mass of charcoal-like substance of carbon is left behind. Yeah, sugar can be converted into a black lump if you have conch sulfuric acid. No, don't try this at home. Don't try to get it from the school lab. The steam of water will just escape, or some of it will be absorbed by the conch sulfuric acid. So this inspires us that even if we don't see a path ahead, if we really have the passion, we can create a path. So yeah, conch sulfuric acid acts like both a drying agent as well as a dehydrating agent. It's a king of chemicals. Even alcohol can be dehydrated and converted into ethene with the help of conch sulfuric acid. And as I told you earlier, if you add it to blue vitriol, it will become white powder because the water will be absorbed by it. Drying agents are also called desiccating agents because they are used in instruments called desiccators. Desiccators are simply equipment in which you can dry stuff like gases which are made in the lab. Water can either be hard water or soft water. Soft water lathers easily. It lathers soap easily. But the soap doesn't lather in hard water. You see, hard water has certain salts, soluble salts dissolved in it, which react with the soap, waste the soap, form some precipitate called scum which can spoil the clothes and doesn't even lather. So we can't use hard water to wash clothes with soap. Yeah, detergents will work. So detergents can be used even with hard water and soft water. But then the hard water cannot be used in industries where water is being used in some equipment or even to make tea in a kettle, because these salts in them, slowly they will deposit inside that equipment and spoil it. So we should know how to convert hard water to soft water. First of all, mark the definition of hardness of water. And remember, the hardness is because of 6 salts: calcium and magnesium off. That is bicarbonate, sulfates and chlorides of calcium and magnesium. So 6 salts. If any of these salts are present, it is hard water. But how do these salts enter the water? Well, because of rainwater or because of any other flowing water. Mark these as read. If the hardness is because of bicarbonates, it's very easy to remove them. Just boil it When you boil it, the bicarbonates will decompose to give you carbonates, which will be insoluble. You can filter it out and throw away, and what is left is soft water, temporary hardness. But permanent hardness means it is not that straightforward to remove it. It's because of these four salts. Heating won't decompose them. You'll have to add washing soda, because then double decomposition reaction will take place. The respective carbonate will be produced. You can filter it out and throw it away, and then you will be left with soft water. In fact, this washing soda method can be used even for bicarbonate. So even temporary hard water can be made soft using washing soda or zeolite, but zeolite is not in syllabus because heating, boiling is anyway a waste of fuel and time. This is cancelled. You see, soap is a stearate. The actual formula is very complex, not in our syllabus. And hard water reacts with the stearate to form insoluble stearates, which will deposit on the clothes and form a scum. The last part is not cancelled. That you have to learn. Only the equations are cancelled. So removal of temporary hardness, mark this as read. Equations have to be learned and practiced. Even these equations, learn it, cancel the note. Advantage of hard water. Well, hard water is useful because it has minerals, so it strengthens our bones. It's good to taste as well. But there is a problem. It cannot be used in certain factories. One more advantage of hard water is that it forms a coating of lead compounds around pipes. It prevents lead poisoning in that water. Disadvantages, I already told you, cannot be used in industrial boilers. Just the heading is enough. Cancel this part. Cancel the diagram as well. Again, learn the heading. It causes corrosion of boilers. Cancel this. It can cause explosion in boilers. Cancel the theory part. It causes wastage of soap. Cancel this. It gives a dull appearance to clothes. Cancelled. Solve the chapter review entirely. Also solve this exercise on page 132, 133. Notice there's some cancellations in this. Even here there's some cancellation. 134 as well. Solve it. Some cancellation here. Hi students, this is AJ sir. If you found this video useful, press the like button. Also, if you'd like to enroll for my test series or online lectures, email me or message me on Instagram. Check my description for more information.